This is a brief introduction to waves and how waves work. So we're going to start by discussing what waves are. So a wave is something that transfers energy. So that's the most basic definition of a wave, is something that transfers energy from one place to another. Now there are two ways to do this. Number one, we could do a particle. And this is just like where we can this is what we've been doing up to this point, right? If you throw something, you transfer energy. So if I want to get energy from one place to another, I can pick up an object, I can throw it, and I can give it energy, and then whenever that object hits something else, it transfers the energy to that person. Think about throwing a baseball at somebody, right? Whenever you throw the baseball, you give it energy. When it hits them, it transfers the energy into them. The second way to transfer energy is the wave. And this is what we're talking about now. The important thing with a wave is that it doesn't actually transfer material. It just transfers the energy. So while material may move back and forth, it does not move toward the other object. So if I made a wave to transfer energy from one place to another, the actual particles would not move. Now there are three types of waves. The first type is a transverse wave. Transverse waves are the ones that we are most familiar with seeing, but they're actually only used in these two situations, light and ocean waves. These are the two, not only two, but these are the two we need to know about, ocean waves. We could also do string waves that we've done. And what you have here is a wave that looks like this. And the important thing to remember here, or to know here, is that the particles within the wave are going to move up and down. And this is going to be the direction of motion. But then the energy transfer is that way. Okay? And so you should notice that the energy transfer, it goes that way. And what this means is, the thing to remember for transverse wave is that motion is at a right angle to the energy transfer. Okay? So that's what a transverse wave looks like. The other type of wave, or another type of wave, is a longitudinal wave. Longitudinal. And this type of wave is difficult to draw, but this is basically sound waves. They travel like this. But this is the way it looks in general. You have areas that are rarefacted, and then areas that are compressed. So these are areas of compression, and these are areas of rarefaction. Rarefaction is where they're split farther apart, and compression is where they're closer together. And this is how the wave is manipulated so that we can actually hear things. Is we have areas where the particles in the wave are compressed, and areas where they're rarefacted, and that's how you actually pick up on sound. So the important thing to note here is that the motion is back and forth, as is the energy transfer. So motion of each particle is back and forth, and energy transfer is also back and forth, or is also in the same direction as the motion. So here, motion is parallel to energy transfer. Alright. So now let's talk about, last type of wave. This is just a quick wave. Torsional. Torsional wave is a wave that is a twisting wave. Google Tacoma Narrows Bridge. So if you want to see an example, Google Tacoma Narrows Bridge, and that's an example of a torsional wave. Alright, so some basic wave structures. Now generally we use a transverse wave to show basically all waves, because obviously it's really difficult to draw a longitudinal wave over and over again. This right here would be extraordinarily annoying to draw. But this is fairly simple. I just go up and down. So what we're going to do is we're going to draw a regular transverse wave, and I'm going to label some parts so that you can have them for examples. Alright, so first thing we need to know is that there is usually a midline that passes through the wave. And where the wave touches these points, there it touches the midline, these are known as the nodes. Okay? And a node is where there is no movement. Alright, then in addition to nodes, we have what are called antinodes. And antinodes are at the maximum places of movement. So an antinode is maximum movement. Okay? I'm going to rewrite that because it looks a little weird. So an antinode, alright, is where the maximum movement is. We should also point out that this is the trough and this is the crest. Okay? Let's see if we can get a T there. There we go. Alright, and then also this is known as the amplitude. And the amplitude is the distance from the midline to either the crest or the trough, so this is also an amplitude. And it should be noted that the amplitude does not affect the frequency or wavelength. And we'll talk about these two characteristics in a second. Alright, so this is the most basic characteristics of the wave. Then let me redraw the wave again. So we have another wave. And there's three more things we need to talk about. And the first of those things is how to figure out the wavelength. First of all, the wavelength is given by the Greek letter lambda. This is the wavelength. It is generally measured in meters. So we have the wavelength. And the way you calculate the wavelength, there are three ways. Number one, 3 nodes. So from here to here to here is one wavelength. Okay? Or, number 2 is 2 crests or 2 troughs. Okay? So from here to here would be one wavelength, or from here to here would also be one wavelength. And then last but not least, you could have the third way is 2 consecutive points can equal a wavelength. So if we wanted to go from here to here, both of these, notice, are going up and over, and so we know that that is 2 consecutive points, and that is also a wavelength. Okay? So that's wavelength. Then we have 2 other terms. The first of these terms is known as the frequency. And frequency is measured in hertz. Symbol is Hz. And frequency is the number of wavelengths per second. And then we also need to know the period. And the period is the number of seconds per wavelength. Alright? And we need to know that the period equals 1 over the frequency, and the frequency equals 1 over the period. They're reciprocals. They are inversely related to each other, and the period is measured in seconds. Okay? So we got wavelength, frequency, and period. Next thing we need to know is the speed of a wave is determined by the medium. So the speed is determined by the medium. And we need to know how to calculate the speed. Well, the formula for speed is d over t. Well, the distance for a wave would be a wavelength, and the time would be the period. Okay, but we learned that the 1 over the period, these two things are equal, right, because t is on the bottom. We learned that 1 over the period is equal to the frequency. So we're going to write this as velocity is equal to lambda f. Alright, period equals 1 over the frequency, because 1 over the period is equal to the frequency, and this is 1 over the period, plug in its frequency. So you'll need to know this formula. Alright, what this means is that if the medium stays the same, the frequency has to, if you change the frequency, you have to change the wavelength. So if the frequency goes up, the wavelength has to go down, and if the velocity stays the same and the wavelength goes up, then the frequency has to go down. Alright? By that same token, if we change the medium, alright, and there's many ways we can do this. One is by stretching a string or stretching a spring or making them more taut. You can change the wavelength by making the air denser or by going from air to water, numerous different ways. But if we change the velocity and the velocity gets bigger and the frequency stays the same, then the wavelength has to get bigger. And if we change the velocity and it gets smaller and the frequency stays the same, then the wavelength has to get smaller. Alright, so these are two different ways to look at speed. Again, speed is determined by the medium. The medium is the substance through which the wave is passing. And then the last thing we need to know, a couple little extras. Modulation is changing a wave to communicate. And also, we need to know about what is in phase and what is out of phase. In phase is when the waves add together. So these two waves are in phase because roughly their crests and troughs line up. So if we were to add waves 1 and waves 2, we would get a bigger wave. Out of phase simply means that the wave is not in phase. So like this is out of phase. Okay? Out of phase and in phase. Now, there is 180 degrees out of phase. Alright? And so 180 degrees out of phase looks like this. And that would be where it goes up and then down and then up. So if this is wave 1 and this is wave 2, these are 180 degrees out of phase, and the resultant would be a null line. Okay? Okay, very good. So we've got all of that taken care of. Now, obviously there were many more demonstrations that we did in class. If you'd like to see some of them, feel free to come up and talk to me. I'll see if I can get one set up for you. But this should get you caught back up in general to where we were on when we started the unit. All right? So I hope this helps.